Supervisors in this particular one were Jonathan, Mark, Ole, and Alexander. So remember, 25 minutes.
Yes.
I will advise you. I will tell you 10 and 5 minutes in advance.
Okay.
Okay. So thank you.
Thanks, Isaac. Thanks for introducing me. So, as Isaac said, the topic of my talk today is inequality, poverty, mobility, and mix. In fact, if I were to suggest that the title of my topic, I would just compress it a little bit and just say that we will be speaking about inequality and mobility because poverty and mixing appear as a byproduct of these two processes. To motivate my contribution in this project, I will first try to define what are inequality and mobility in the world and try to illustrate how their dynamics appear in the real world. First, both inequality and mobility are related to the concept of wealth. They are functions of wealth. By wealth, here we will try to think about our monetary or valuable possessions that we have. Some people can argue that maybe under wealth sometimes we have something that is like the human capital or our health status, etc. But here we'll just stick to defining wealth as the abundance of valuable possessions or money. Inequality is a static concept that tries to uncover the positioning of wealth among the different people in the population. It just measures the extent of the concentration of the distribution of wealth among the population. To better understand what we mean by distribution and by the concentration of distribution, let us just see one distribution of wealth. So here on the x-axis we have the wealth, and on the y-axis the proportion or the frequency of people in a population that have that amount of wealth. One can easily argue that here wealth is, there is not a big concentration among the wealth in the population because the mass of the distribution is centered around the mean value. However, this is not a strictly realistic case. In reality, the distribution of wealth looks more or less like this. That is, that there is a small amount, there are few people which own a large proportion of the money in the world. On the other hand, when we try to describe mobility, mobility is a dynamic concept. It tries to uncover how the wealth of one person evolves among the distribution of the wealth during different time spans. To understand this concept, let us look again at the second distribution and try to add a subscript t. Now we measure the wealth over a period of time t. And here, for example, we have the amount of where an individual I was positioned at time t. And by mobility, we can understand something which is changing. In t plus 1, the wealth of the individual I moved to around the mean of the whole population, and one can understand that he may be mobile under this distribution. Now let us see how inequality and mobility fare in the real world. First, I would like to introduce a figure. This is a figure by Adamo and Peters from their paper in 2016, where they just plot the different indices of wealth inequality. Actually, this is income inequality, not wealth, but we can, just for illustrative purposes, we can skew this. And here we can see that independent of the measure that we get, every measure suggests that inequality is increasing over the time interval. I'm just pointing out the time interval between 1970 and 1995 because, as you will see in the next figure, where we try to compare mobility around the world, we just have the time span from 1970 to 1995. Here, in this plot, we just try to see how different indices for wealth mobility, or here again income mobility, show how mobility moves in the real world. One can say that independent of the wealth measure, this is data for the US, by the way, and these are measured at time intervals of 11 years. So every index is computed by comparing the distribution of wealth at time point t and at time point t plus 11 years. So independent of the mobility measure, we can observe that there is practically static dynamics, that mobility is stable over time. However, I would like to point out about how all of these measures are created. They compare the distribution of the whole population with the distribution of the whole population at different time intervals. So they don't look at how a typical individual moves. So mobility in this sense can exist if only just two people move in their rankings of the distribution. And one can say, yes, we have mobility, but in reality only just two people move around. In short, let us summarize this concept. So, irrelevant of the measure, inequality, we observe that inequality is increasing over time. However, also irrelevant of the measure, mobility is stable. However, we observe that the magnitude of mobility, which is measured in percent in every here index, is different depending on the measure. And this raised a lot of discussions in the economic, in the politics. I wouldn't like to mess around that. I just want to say that here is one sentence from a person who works at the Fed. He says like, hey, mobility is high enough. We have high mobility. However, other economists may say, you know, we have income mobility, but that income mobility is not enough. So here we would like to ask, what is the realistic level of income mobility and how would someone would actually measure it? So if that is even possible. So therefore, the contribution of our project here was to explore the relationship between inequality and mobility in a simple model of wealth dynamics. And here we would like to introduce another measure of measuring wealth mobility by trying to introducing mixing time. Mixing time is known in physics as the characteristic time over which, for example, over which particles mix among the distribution. Here, we try to measure the mixing time in the distribution of wealth as the characteristic time over which individuals mix into the wealth distribution. One can find a synonym in this concept as one tries to mix milk into coffee. For example, you can see that the individuals that we try to explore can be the milk, and the distribution of the wealth can be given by the coffee, and we want to see how people disperse over or spread out how the milk spreads out in the coffee when we try to pour it over. So first, before we talk about mixing time, let us see the simple model of wealth dynamics. Here, we describe the simple model of wealth dynamics through reallocating geometric Brownian motion. Under this model, we assume that the dynamics of wealth of an individual follow a multiplicative process, which is driven by a drift term mu and the noise amplitude sigma. And after the growth process, or before the growth process, there is a additive term which acts as a relocation from the poor to the rich or to the rich to the poor, depending on the relocation parameter tau. For example, tau greater than 0 can be seen as a taxing scheme for the people that have above average wealth, and can be seen as a subsidy scheme for the people that have below average wealth. To better understand the reallocation GBM, let us look at the rescaled wealth. This is a dimensionless quantity where the wealth of individual I is just compared to the average wealth in the population, or the mean wealth in the population. When we have tau greater than 0, or as we said, when we have something which acts as a reallocation from the rich to the poor, then for the stationary wealth, we get something which resembles a stationary power law distribution of wealth. This is something which is observed in nature, and this is exactly the same red distribution that I saw you in the first few slides. For tau equals 0, we recover the GBM dynamics. For GBM dynamics, we get inequality increases over time in terms of wealth, and there is no stable distribution for the rescaled wealth. In the end, it ends up that one person owns all the wealth in the population. For negative tau dynamics, we observe something which is non-ergodic. In this sense, we can observe some people even having negative wealth. That means that some people in the population go into debt, which is far more realistic than the positive tau and the tau equals 0 dynamics, when there is no negative wealth between the population. And in reality, there are a lot of, for example, there is, of the 20% people that are in the lowest quantile of the US wealth distribution, most of them have negative wealth just because of that debt. And this non-ergodic, this non-ergodic wealth dynamics induces a lot of implications which can be discussed even further. And then in the economic terms, which is traditionally used, people cannot use the rescaled wealth as a, okay, we have the rescaled wealth, let us study now the stationary properties of the distribution of the population, etc. And I would like just to point out that there is, in a finite population, there is time scale for self-averaging of the dynamics of this equation, which is proportional to the magnitude of tau and the population size. That is, after a certain amount of time, the single individual dominates the average of the wealth. And in other words, one cannot strictly assume that the average wealth is given by exponential of mu tau, which is just the expectation of under geometric Brownian motion. To see how this RGBM fares in the realistic population, here we have a figure from the paper of Berman and his co-workers, where they try to fit tau of t, which best reproduces the wealth share of the richest 1% in the US population. Here, one can observe that over time, we are currently in a regime where there is a negative tau. In other words, there is relocation from the rich to the poor. And again, we get these implications where we're in a non-ergodic regime, and one cannot simply define inequality. Inequality is increasing over time, and mobility is what we try to explore in the next few slides. Here, we start with the Spearman correlation, which was one of the measures that were plotted in the realistic dataset, where we compare the Spearman correlation between the wealth x at time t and the x at time t plus delta. For visualization purposes, here we chose just delta that to be equal to 10, and we have some parameters. The population size is 10 million, and there are other parameters for the drift and the amplitude of the noise. So what we observe in positive tau regime, we observe that after a certain amount of time, the Spearman correlation, enters a steady state, and it remains the same afterwards. So here, I would just like to point out that lower Spearman correlation implies greater mobility in the population. However, when we try to introduce negative tau, something weird happens. So first, we get an increase in the inequality, then we get a decrease, then something which looks like it's converging to a steady state, but after that, we get everything that moves around. So this is actually the point where self-averaging ends. So in this case, after the self-averaging ends, the population average wealth can be negative, and this may lead to mobility between only certain groups of the individuals. Not every individual can move across the distribution, but only certain groups which are, some people can leave the third quartile, enter the one bigger quartile, and then vice versa. So one can argue that maybe the correlation or ranking scheme is not good enough to present mobility in the negative tau regime. Therefore, we try now to see that here we just plotted for different tau values, the Spearman correlation for negative tau at different points in time for negative tau and for different values of positive tau. And here one can easily conclude, I don't have that figure, but we can easily conclude that the Spearman correlation decays exponentially with tau. In positive tau, we get that larger tau, larger reallocation from the rich to the poor, there's more mobility in the world. Whereas it also decays proportional to sigma, so this graph would be just switched to the left when there's different sigmas. However, for negative tau regime, we don't understand what's happening, and we just decide, we're saying that this will be to be decided and to be determined in some future work. But here we would just like to say that mobility is not among the whole population, but just among certain subgroups of the population. So here, now let's define mixing time in more detail. So again, I'm repeating myself. Mixing time is the characteristic time scale over which the individuals mix into the population. So we assume that there is a steady state distribution. Therefore, mixing time can exist only for tau greater than 0. This is the first point which we want to point out. Then, how do we measure mixing time? We just initialize a population with a stationary rescaled wealth distribution. That is the power law distribution that we showed, the red line. And then we select a subsample which is closest to the mean. This can be either one individual, or it can be a certain amount of individuals. Here in the simulations that I will show you later, we just select the subsample to be the 1% closest to the mean. One can see that the population, when we initialize the population, this is just we are making our coffee, selecting the subsample, we are just pouring the milk into the coffee, and then we simulate the wealth dynamics, or we just move the spoon around with our coffee and try to discover how the milk spreads over the coffee. So to measure how the milk spreads over the coffee, or how the subsamples. Then we do a regression line where we estimate the slope of the log of the KS statistic on time. And until the log of the KS statistic saturates, I will show you this in a video how we exactly do that. And we just measure mixing time as -1 over the slope of the vector regression. Next is the video which I would like to show you. So here I would just like to, here we will get here the KS statistic over time. The red dashed line is the distribution of the subsample, and the black line is just the distribution of wealth among the population. And here you can see how this evolves. One can easily see that. One can just easily see that the distribution converges to some distribution of the population, and the KS statistic actually converges to some somehow to some similar value. Do you understand this, or I have to go once again through the video? Okay, let me just. I need to. So here we have the subpopulation distribution and the wealth distribution over time, and the KS statistic how it converges over time for the whole sample population. One can easily notice that after a certain amount of time, the distribution of the subsample is exactly the same as the distribution of the population. So, oh sorry, I have an extra here. This is small. What is the dependence of mixing time on sigma squared, or the variance of the noise, and dependence on tau, or the relocation parameter? Here, the dependence on sigma from this figure, one can easily notice that there is no dependence on sigma, and other numerical simulations also confirm this, but nevertheless, we're still curious of whether this is true, therefore we just say this is to be determined. And the slope here of the log of t as a function of the log of the convergence time is just -1, so one can easily notice that the mixing time scales with 1 over t. So in our model, one can understand the mixing time, or the measure of mobility in an RGPI population, is just 1 over t when the stable distribution is sorry. And as an application, consider the Great Gatsby curve. The Great Gatsby curve was introduced by Kruger in 2012, where he tried to measure, to invent how inequality and here is mobility compare with each other in the world. So we have countries with larger inequality, also have larger, here on the y-axis is immobility, so that's the inverse of mobility. They're less mobile. And one can easily notice that this is an increasing function of inequality. And in our model, that is easily reduced if we try to measure immobility as 1 over tau, or the mixing time. And here, for simplistic reasons, we just measure the variance of the rescaled wealth as our inequality measure. One can also use different types of measures. So one interesting thing here is that here the linear is somehow linear, but in the RGPM model, essentially the relationship between inequality and immobility is somehow concave. And in short summary, here we studied the relationship between immobility and inequality in a simple model of wealth dynamics, and one can easily say that the non-ergodic dynamics of the wealth essentially makes the time very important as a crucial ingredient in deciding what is. We don't capture how a typical person moves across the distribution if the stable distribution exists. Mixing time, on the other hand, allows us to capture this this concept is thin. And we found that in an ergodic regime, mobility is strictly determined by the magnitude of well reallocation in terms of mixing time. Bigger tau, larger reallocation, lower mixing time, that means more mobility and more population. However, in the non-ergodic regime, mixing time is just one of the factors. There's no possibility that